So thank you very much, everyone. It's great to see so many people here. And I'm hoping that tonight I'm going to send your mind spinning with potential ideas of how you could use the technology and hopefully show you something memorable that you'll take away with you tonight. So I'm Tom Scott. I like to think of myself as a professor of materials and devices, mainly because I like the acronym that comes with that. But most of the time, you can wait for the catch up on that one. Most of the time I spend looking at the behavior of materials, usually radioactive ones, in the environment with respect to understanding how we can protect our environment in case they're released unexpectedly. So Diamonds Are Forever is inspired by the fact that our world is changing around us. Since the start of the Industrial Revolution, we've been burning fossil fuels at an alarming rate, and that rate has got faster and faster. And we're pumping carbon dioxide into our atmosphere very, very fast in million-ton quantities every year, and that's causing our global climate to change. And we see that in the UK because we're getting warmer, we're getting wetter, we're having more extreme weather events. And so I'm very much an advocate for low-carbon energy technologies. And in fact, I head up for Cabot the theme of low-carbon energy. Now, one of the tools we have in that arsenal of low-carbon energy technologies is, of course, nuclear energy or atomic energy. And it's a technology when you compare to wind or solar, which has a lot of maturity. It's got thousands of operational hours. And because of that, we're very familiar with it. In fact, the UK was the first country to have a civil nuclear reactor. We were the first country to have the first nuclear test reactor, which was called BEPO. And so we've had 60 years of experience in nuclear power generation. And nuclear power generation is carbon neutral. It's carbon free. We don't produce carbon dioxide by using a nuclear reactor, and that's a good thing. But obviously it's a controversial energy source because a small number of accidents have got very, very high profile. So Fukushima in March 2011, I think everyone's familiar with, a nuclear disaster. Well, that incident has yet to claim any lives in terms of radioactive poisoning, radioactive death, radioactive-induced cancer. And in fact, more people died because they were forcibly relocated. Over 1,000 people have died because of that, and nobody yet has died from the radiation. And yet, it's high profile. It's regarded as a disaster because of the perception about the danger of the radioactivity. Now, in the UK, we've been running a special type of nuclear reactor that not many other countries have, and this is unique. And this means we've got a unique opportunity that I'm going to tell you about. And our reactors, instead of using water like everyone else to essentially cool the reactor and to cool the nuclear fuel rods, we use gas. We use carbon dioxide gas in a sealed vessel, which we cycle round and around, and that never leaves the reactor core. And also in that reactor core, we use graphite. Now here at my feet, I have a graphite block. And in a reactor core, we have many thousands of these blocks. They each weigh about 40 kilograms, and they're stacked up high, such in a reactor core that I'd be familiar with, these blocks would fill all the way up to the top of the dome and back down. So they're quite large structures, and that's quite a lot of carbon. And in graphite, the carbon is arranged in sheets, and the bonds between the sheets are very, very weak, so it's easy to separate, which is why we use graphite in pencils, for example. And we use that graphite because it slows down the particles which are coming out of the nuclear fuel, and that makes the heat transfer more efficient. But what that means in the UK, because we've been running for 60 years with dozens of nuclear reactors, is we've accumulated a lot of interesting nuclear waste. Some of that's uranium-based, so uranium's my favorite material. Some of that is graphite. And in fact, because of all of our reactors have graphite cores, that means we've got an awful lot of graphite, 95,000 tons, to actually get rid of. Now, the problem with graphite is that once it's been in a nuclear reactor core for 30 years, experiencing the flux of radiation that you get there, and that's an intense flux of radiation, what happens is some of the graphite is altered, and some of the graphite becomes radioactive. And in fact, what happens is it gains some mass, it gains particles, and it turns into radioactive carbon-14. And that radioactive carbon, if you took a kilogram lump of it, for example, and you left it on a shelf, it would take 5,700 years or so for half of that material to have just decayed away and gone back to normal carbon. So because of what we call that half-life, it means that radioactive waste represents a very long-term problem. And actually, for us in the UK and for other countries that have to deal with nuclear waste because they've chosen to have nuclear energy programs, that's a very, very long-term problem that is shared onwards and onwards through generations. And it's about managing safely that legacy, which is very, very important to me, and it's very important to the Cabot Institute. As I said, graphite is one specific form of nuclear waste that we have to deal with. Relatively speaking, it's quite clean because most of the radioactivity comes from this radioactive carbon, but there is a lot of it. Now, we've got plans in the UK for a geological disposal facility to put all of our high and intermediate level nuclear waste underground, and there's so much graphite that that would take approximately 1/3 of the volume of the planned geological disposal facility, which is an awfully big space. And when you think how many tens of billions of pounds that will cost, then we can think of our 95,000 tons of graphite as, for us as taxpayers, it's going to cost us something in the region of £20 billion to deal with. So I like the idea that we can think of it as a waste, we can think of it as a problem, or we can do something completely different. And that's where my story comes in. So let me just give an example for a second. I'm going to call in one of my helpers, Dr. Liam Payne. And if we think this 95,000 tons of graphite, I can't transport all of you to a nuclear reactor, so I thought I'd bring a little bit of graphite from a nuclear reactor, a real graphite from a nuclear reactor, and demonstrate just how radioactive it is. So there's a small amount of graphite, about the size of my thumbnail. It's about 3 millimeters thick, okay? Liam's got a Geiger counter, which will make a noise, and the crackling noise is proportional to how much radiation. So Liam's putting it over the top, and you don't get very much, okay? Get about 100 counts a second. And what he's measuring is gamma radiation coming off. But that gamma radiation is actually not coming from the graphite. It's coming from metal impurities, which have also become radioactive. Now, Liam's now taking the plastic cup off the top, and he's going to show you the radioactivity of the carbon-14. So I think we can all appreciate. So we went from having 100 counts a second to about 2,000 counts a second. And that was the radioactive carbon. And it's not in its radioactivity like X-ray radiation that we'd be familiar with from a hospital. It's actually emitting high-energy electrons that we call beta particles. And they don't actually travel very far in air, so it's safe for me to stand next to that. And we can block that with a bit of plastic, with a bits of perspex. But we think we have 95,000 tons of this stuff, which is crackling away. And I can show you a bit the size of my thumbnail, and that's giving you 2,000 counts a second. It gives you an idea of just how much energy is stored in this material as a function of its exposure over its lifetime. So what are we going to do with it? So what we plan to do with it, which is something different, rather than just think of it as waste and stick it underground, we want to extract the carbon-14. And we want to turn it from graphite into something which is a bit more valuable. Okay? This belongs to the Pro-Vice-Chancellor. I should give it back again. But to turn the graphite into diamond. And diamond is a wonder material. And it's a wonder material because the way that the carbon is arranged in its three-dimensional architecture is such that all of the carbon atoms are incredibly strongly bonded to each other. And those bonds are some of the strongest bonds that you can find in a material. And so when you expose it to temperature or to pressure, it can withstand it. It's the hardest material naturally that occurs on the Earth's surface. And that means in a high radiation environment, it's very difficult to break it or to damage it. And for most materials that we could put in the core of a nuclear reactor, they will degrade and they will start to fall apart. So if you put a camera in a nuclear reactor, it will last about 2 seconds before it breaks. Diamond doesn't break. So that started with the fact that this diamond, as well as being super hard, it's also what we call a semiconductor material, in that we can play with the electrons in this material and we can actually use this as a type of radiation detector. And this is what we've been doing with our friends up at Sellafield, because they have some nuclear waste environments which represent the most hazardous environments on the surface of the planet. So we're talking doses of radiation which would be up to about 2,000 times the lethal dose, okay? And they have problems measuring the radiation because when they put the radiation detectors in that currently exist, they break within seconds. And so diamond represented an opportunity to add a material which could act as a detector material, but it was also invulnerable to the radiation. And we developed a detector system which essentially, every time a radioactive particle hit the diamond, it would generate a little pulse of electricity. And when that radiation is really, really intense, so you imagine as if you're standing out in an intense rainstorm, that detector is being hit many, many thousands or even millions of times a second. And instead of just generating a little pulse, it generates a constant current. It generates electricity, okay? And this became our inspiration because we use this as a detector, and we use this regularly at Sellafield now. This is their favorite new toy. But actually what we've shown to them is we can use our diamond detector not just to detect the radiation, but to generate electricity from the nuclear waste. And the more radioactive the nuclear waste, the more electricity that we can generate. Now that's really good if you're willing to go into a lethal radiation environment and install lots of diamonds everywhere, but it's quite difficult, and I need some expensive robots, and I haven't got that money yet. I'll look at the Dean of Science for that. But the idea for us is that for this graphite, when it's nuclear waste, per cubic meter, it will cost you as taxpayers £43,000 per cubic meter to safely manage and dispose of that waste material. Now, imagine if we could develop a process, and Liam, who brought this on, has developed a process to do this, that we can process this graphite to selectively remove the radioactive carbon, and with that radioactive carbon removed, that block of graphite counts as lower level waste. And instead of costing £43,000 per cubic meter, it costs £3,000 per cubic meter to deal with. So tick on that one, save the taxpayer a lot of money. But what if we do something really useful with the radioactive carbon-14? What if instead of using normal carbon to make our diamonds, we use radioactive carbon? And we form the world's first highly and deliberately radioactive diamond. And in doing that, we can make our energy harvesting device much, much more efficient because the radiation is being developed inside the diamond, and its efficiency is near 100%. It's about 97, 98% efficient. And we can do that by a controlled heating in a special system of the graphite to drive off the radioactive carbon-14 into a gaseous phase. We then capture that gas, process that gas, turning it into radioactive methane, and from that methane we can use a technique called chemical vapor deposition, which basically, at high temperature but low pressure, we can grow diamond. And we do that in the chemistry department. We can grow diamond, and we do that every day of the week. And surprisingly, it doesn't cost thousands of pounds. It costs £5, £10 to grow a diamond. In fact, we're going up to diamond wafers, which are about 8 inches across and a couple of millimeters thick is what we're planning for in the next year or so. So by growing radioactive diamonds, which has never been done before, we can start to think about growing tiny batteries which have essentially a half-life of 5,000 years. So I think everyone this morning or last night, when they were thinking of work and thinking about the fact they'd need their mobile phones, everyone plugged them in, okay? I need to recharge my phone. It's the most annoying thing in life, is recharging my iPhone. So imagine if you could have a tiny little power cell which constantly gave you out a small amount of current, and you could stack these cells just like a real battery to give you higher amounts. What could you achieve with that technology? Well, first of all, you might be wondering, you've made a radioactive diamond. We have to be careful because it's radioactive, okay? So the one thing we can do with that diamond, and we need to do to make the technology work, is actually we sandwich it in normal diamond. And the reason for that is the normal diamond will not only shield that radiation and not let it out, but it also increases the efficiency of the energy generation. And so by making that sandwich, we have the radioactive carbon-14 on the inside of the sandwich and the normal carbon-12 on the outside of that sandwich, and hooking it up via electrodes, we have our tiny little diamond device. This isn't just an idea. This is something already. We have a prototype in the lab in the chemistry department where we have proven that this will work. And we've proven with a tiny little device which can generate a constant current that this really is a technology we should and will develop. And the best thing is, on the outside of the diamond device, it's got less radioactivity than a banana. Okay? But bananas don't have too much radioactivity, so don't worry if you had one this morning. So we're moving towards tiny power cells, which have no external radioactivity, but give you a constant but small energy output. You can sum them together to get higher amounts of energy out. And that gives the possibility for lots and lots of different things. There are some obvious ones, but I want you to think about the less obvious ones, the ones I haven't thought of yet, because I tend to think about devices. But for humanitarian aid, you can think of hearing aids being an obvious one, a hearing aid where you never need to replace the battery. You can think about implant devices like pacemakers. The current alternative for pacemakers is to have plutonium-based pacemakers put inside you. Plutonium is the most toxic substance on the face of the earth. So the idea of putting that inside me when I'm old and I've got a dicky ticker is not one that I'd prefer, you know? Even to the fact I've got a new cat. Could I put a small nuclear power device in the cat so it has a tracker on it, okay? Or you can go a bit more James Bond if you want. Of course, possibly you can get to the point where you don't ever need to recharge your mobile phone. And the greatest thing to think about is if you have a device like that, it will still only have got to 50% of its power output in the year 7,700 or so. Okay? So it represents a lot of capability for long-distance space travel, but I prefer to use that technology on Earth when it can get its best possible gains. So with that, I'll leave you thinking, I hope, and come and talk to me afterwards with your ideas as to what you could do with a technology like this. Okay? Could you bring, for example, internet to developing countries by powering high-altitude drones that can constantly circle over countries in areas where there is no internet by landline? Could you do that? Yes, you could. So come and talk to me afterwards. I hope you've enjoyed seeing a bit of real nuclear reactor and listening about batteries. Thank you very much for your time.